Maximum power transfer already had a clean DC rule. Match the load resistance to the source resistance seen from the load, and the delivered power is maximized. But in AC circuits, impedance has both real and imaginary parts. So the matching rule also has to grow into a complex form. In DC, the condition is simple. R load equals R Thevenin. In AC, we no longer match with resistance alone. Instead, the load impedance must become the complex conjugate of the Thevenin impedance. That is the AC maximum power transfer condition. Suppose the source side looks like 4 plus J3 ohms. Then the best load is 4 minus J3 ohms. The real parts stay equal, while the imaginary parts cancel. That cancellation is the key reason the total path becomes most favorable for real power transfer. Now, apply that rule to a Thevenin source. If V Thevenin is fixed and Z Thevenin is 4 plus J3, then choosing Z load as 4 minus J3 makes the total impedance purely real. The current becomes easier to interpret, and the load receives the greatest possible real power from that source. Write the total impedance as Z Thevenin plus Z load. That becomes R. Thevenin plus R load plus J times X Thevenin plus X load. When the load reactance is the negative of the source reactance, the imaginary part disappears. The source no longer wastes effort supporting a leftover reactive mismatch. Under the matched condition, the maximum real power delivered to the load becomes the magnitude of V Thevenin squared divided by 4 times R Thevenin. Notice what remains in the denominator, only the real part. That is why the reactive part must be cancelled instead of copied. So the AC rule is not equal impedance. It is conjugate matching. Keep the real parts equal, flip the sign of the imaginary part, and the load receives the maximum real power available from that source. Next, we move toward resonance and frequency selective behavior.